Greetings and welcome to this episode 12 of Living Off the Grid in the City. Again, this is your host, Hector Vladimir. Today, October 23rd, 2015.
Edited and updated April 14th, 2024.
Today we have probably a short show because it's more or less an addendum to the last show on solar technologies. I said that I was going to discuss some of the non-traditional or non-photovoltaic solar technologies that I don't fully understand, but I'm familiar with. So I like to share those. And not only am I somewhat familiar with those, but also I am going to soon enough here begin experimenting with those. I invite everyone and anyone that may be able, capable, and willing to experiment with those to do so. And if at all possible, share your experiences, share your
advances
or any kind of breakthroughs with those. And as always, try to help each other out as far as technologies is concerned, especially those that may enable you to get off the grid. Some of the solar technologies that I'd like to discuss, apart from photovoltaics and heat concentrators, are the very seldom discussed and little known technologies of solar thermocouple. Thermocouple technologies go way back, just as photovoltaics go way back into the 1800s. As you may have watched in the Cosmos series,
in 2014,
there was a short introduction to that type of solar technology where in France at a science fair, there was a man,
Augustin Mokat,
whose invention was on display at that certain fair in the 1800s.
According to Bureau International des Expositions, Augustin Mokat's solar device made its debut at Expo 1878 Paris. At a time when France was seeking to rebuild itself from the Franco-Prussian War, the inventor of the first parabolic solar collector was seen as a genius, a brilliant French mathematician who possessed futuristic mentality that led him to foresee a time when the world would no longer be able to depend on non-renewable resources. Mokat first built a solar-powered steam engine using a concave mirror to reflect the sun's rays onto a glass-covered boiler. To his amazement, it worked perfectly and motivated him to experiment further in North Africa. Algeria was chosen as an ideal location for testing, which led to the invention of many solar energy devices, including a solar cooker and a small solar engine for pumping water. Inspired by the successful results, Mokat then created the world's largest parabolic solar collector, which was revealed at the World Expo in Paris in 1878. It was made using specially shaped mirrors to focus the sun's rays onto a black copper container filled with water, thus turning it into steam. This machine was then attached to a heat-powered refrigeration device and used to produce ice blocks. Within its impressive creation using a concentrated solar power for the first time, Mokat won the gold medal. Despite the ingenuity of Mokat's solar machine and his revolutionary book on solar heat and its industrial uses, the idea of solar energy as a replacement for non-renewable resources was swiftly abandoned following the discovery of more coal in France and the discovery of oil in the United States. Today, growing environmental challenges and the urgent need for unexploited sources of energy has forced researchers to review Augustin Mokat's inventions from over a century ago. The refined process, nowadays known as concentrated solar power, CSP, is based on the same principle as Mokat's parabolic technique, combined with thermal energy storage to create energy that is highly beneficial in terms of reliability, independence, and security. With its future energy theme, Specialized Expo 2017 Astana is the place to discover the novelties and sustainable and renewable energy and see how far we have come since Expo 1878 Paris. Again, this was an article from February 15, 2017 by the Bureau International des Expositions. Augustin Mokat
basically displayed an invention that consisted of a solar concentrator, which very curiously made refrigeration possible. It was very curious because from heat, he was able to create and generate a very cold environment, cold enough to make some type of iced drink or iced food. Nevertheless, it was very cold, very cool, and a rather new invention. It's very
spectacular,
especially at the time. The way it works is quite curious as well. It's a certain metal combination, and together with simple machinery, relatively simple machinery and tubing, where heat, not necessarily solar, but he used solar rays, light rays, to concentrate heat into an area and transform that into pressure. As you may know, heat builds up pressure, and that pressure can be used to create a cool environment. As you may also know, as the pressure goes up, the temperature goes down. This is a physical phenomenon that's well known in the physical sciences, and it is something that could be readily used to make such contraption to where you can create cool substances out of a hot medium.
Technologies such as these
have been obscured for the most part, but it has been in use in many industries and in some residential applications such as propane-powered refrigerators, which are for the most part non-existent here in the United States. They're unheard of for the most part. Most people don't even know they exist, but they in fact do, and you can acquire them, albeit for much more than your average refrigerator, for obvious reasons, and because there are much less available. Not because they're much more expensive to build, but only because they are distributed so little that their prices obviously and naturally go up. Your compressor, as you may have noticed, even an electric refrigerator, basically creates high pressures with the help of the electric motor, and that high pressure is used to drop the temperature in a very simple way using freon valves, tubing. Refrigeration works by extracting heat from a certain environment. The more heat you extract,
the colder that environment
turns. The same concept is used in the solar refrigeration technology that I just discussed, and that I will go into detail more about.
A higher atmospheric pressure is used to
extract heat from a certain environment, therefore cooling whatever other medium you may want to cool, such as water, foods,
a material,
or medium like air for air conditioning, air cooling, etc.
Before I go into these technologies, and
just to touch a little bit on the history of solar energy and photovoltaics, first, Alexander Edmund Becquerel, born 1820 and died in 1891, or more simply Edmund Becquerel, a French physicist. He was the first man to observe the photovoltaic effect, phosphorescence. He was the son of Antony Caesar Becquerel,
who also worked in this field,
electrics, as I'm reading here from Wikipedia.
In 1839, at age 19, experimenting in his father's laboratory, Becquerel created the world's first photovoltaic cell. In this experiment, silver chloride or silver bromide was used to coat the platinum electrodes. Once the electrodes were illuminated, voltage and current were generated. Because of this work, the photovoltaic effect has also been known as the Becquerel effect.
Huge discovery. The other scientist that I'd like to mention is Augustin Mokat, which is the scientist that I told you about, who displayed the invention of solar refrigeration at the Universal Exhibition in Paris. This is in 1878.
He was notably recognized for the production of ice using
concentrated solar heat. This is a part of the solar thermal energy type of technologies. This is purely transforming heat into cold. And before I can discuss how a solar refrigerator works, I would like to go over how a conventional refrigerator works. Basically, when you pass the compressed gas
through coils,
which are basically tubes, usually copper tubes of some
length,
zigzagging
throughout the length of the refrigerating surface. These coils are commonly placed in the rear of refrigerators.
The warmer gas can lose its heat to the air in the room. Basically,
the refrigeration fluid, such as Freon,
as it goes through these tubings, it loses some of its heat because of its increasing pressure to the surrounding area. This fact, or this process, cools the Freon, or the HFC, which changes into
a liquid
because of the high pressure.
It
loses further heat, the same as sweat. Your body loses heat through sweat, through evaporation. The same thing happens with the surrounding areas. The surface, it loses heat through evaporation. It has liquid, and liquid is evaporated. It loses heat. Basically, the liquid inside of the tubing evaporates. The tubing itself, the area within the tube, loses heat. That heat is basically
dissipated into the
environment, and the cooler temperatures are maintained and increased within the tubing itself. This cooler air, the tubing, is basically channeled
to the refrigeration area.
Very basically, in one sentence,
per the website How Stuff Works, when a liquid evaporates, it loses heat to its surrounding areas.
If you can picture a coil that is continuous, it doesn't break anywhere, it doesn't have an in or out, it's just tubing that is
continuous, one loop.
Part of the loop is within the refrigerated area, or the area to be refrigerated. It's usually coiled or in a serpentine fashion, basically zigzagging, and that coil continues to the outside of the refrigerated area, usually the back of your refrigerator if you have a conventional refrigerator. And that loop continues and is also attached to a valve, what they call a high pressure valve, and also has attached to it a compressor,
which is a pumping motor to compress the
medium air or the gas that's within it. Also, there is a gas within the coil at all times. This gas could be various kinds, freon,
ammonia, or various types of HFCs.
But for example, let's say ammonia, which is a gas that, according to How Stuff Works,
it evaporates at
negative 27 degrees Fahrenheit
or negative 33 degrees Celsius, which is 273 degrees Kelvin.
Let's say this ammonia gas is within the coil, and it stays within the coil at all times. Since the coil is continuous, it has no breaks.
It has no way to escape theoretically.
Just picture that. The cycle is a refrigeration cycle that begins with the compressor. The compressor compresses the gas, the ammonia gas, in effect raising its temperature and pressure. When you raise the temperature of ammonia, for example, it will turn into a liquid state. So the compressor basically compresses the ammonia gas, turns it into a liquid, and adds pressure to it. Remember, the compressor is both pushing and intaking liquid and vapor. This high pressure liquid continues down the tubing or the coil,
where it is
coiled or channeled to the valve. The high pressure liquid within the coil goes to the high pressure valve, which is basically a small hole where one side is high pressure liquid ammonia in this case, the other side. So on one side is pushing the liquid ammonia out, and the other side is sucking in effect, the
ammonia vapor
or the gaseous ammonia in. So the valve itself has two sides. Of course, it has the high pressure side with the liquid ammonia, in this case, being pushed into the valve by the compressor. And on the other side, the low pressure side, the ammonia is leaving the valve, being sucked in by the compressor on the other side. And it's leaving the valve. As it leaves the valve, the high pressure valve, it turns again to
vapor, and
it begins to cool because of the high pressure effect of the valve. As it releases the ammonia on one side, on the other side, the low pressure side, the ammonia expands rapidly, thus losing temperature and going back to its gaseous state. Remember, at negative 27 degrees Fahrenheit, it begins to turn into a gas again. Thus, when liquid turns into a gas, basically it sweats, it evaporates, and just as sweating, the evaporation of water on your skin cools your skin, again, this evaporation process cools the tubing to a very low temperature, thus producing
refrigeration.
That coil, which carries that cool evaporating ammonia, of course, is coiled and placed within the refrigeration area or in contact with the refrigeration area, thus making that refrigeration area lose heat as well. Thus, the cooling effect basically is transferred via contact with either air or direct contact with these coils or the refrigeration area. The refrigeration process using a compressor is very similar to the solar side of it, the solar version of the refrigerator, this solar refrigerator. And I will go into a little bit of detail for that. The only thing that is
replaced,
among others, the main thing that is replaced is the electric compressor. And in its place is put a boiler, which is powered by solar heat radiation. The other very simple solar refrigeration technology that has been developed again for many, many decades in the 1800s, as I mentioned earlier, was also introduced in 2009 by a British student, Emily Cummins. The basic construction of the refrigerator is quite simple. It takes nothing but the use of a metal cylinder, an inner metal cylinder, and an outer plastic cylinder. In between those two cylinders, those are sealed cylinders on one side at least. Between these two cylinders, there is a medium or substance such as cotton, sand, some type of organic material, preferably. The material could be wool, sand, dirt, any type of organic material that could absorb water and readily evaporate it, allow its evaporation. You basically pour water into this organic material in between the two cylinders and close the cylinders on top, preferably with an insulated lid, and place it in the sun as the outer area of the outer cylinder is heated with sunlight. Evaporation of the water inside occurs inside of the organic material, and of course when evaporation occurs, cooling happens. Cooling is in contact, of course, with the inner metal cylinder, thus cooling whatever items you may have inside for cooling. This is sometimes used for cooling medicine, water, vegetables, fruits, or any type of food or drink. The concept for these refrigerators go back to ancient times in ancient civilizations of the Middle East. However, the concept could be used readily for off-grid applications, especially in hot, dry, and remote areas of the world. The construction of this refrigerator is very simple. You may also build it with a pair of terracotta vases and put sand in between the bigger and smaller vases and add water to the sand. Place the contraption in the sun when it's dry, and the content of the smaller inner vase should be a lot cooler. It says on the article that I read, a temperature of 43 degrees Fahrenheit could be achieved for up to 2 days with a single water replenishment. Since it's not a hermetically sealed contraption, water will evaporate out eventually. But this, as you can tell by the 2-day expectancy, that is a very slow leakage, thus making it a attractive and a effective technology to help you get off the grid and use electrical free refrigeration. Thermocouple refrigeration is a little bit more of a complex phenomenon, which I will attempt to explain here shortly. And it basically relies on the combination of some exotic metals, which may or may not be accessible to a good amount of people wanting to get off the grid. And since I have limited understanding of the thermocouple effect, I will be reading an article from wikipedia.org on the subject. The thermo-electric effect is the direct conversion of temperature differences to electric voltage and vice versa via a thermocouple. A thermo-electric device creates a voltage when there is a different temperature on each side. Conversely, the voltage is applied to it. Heat is transferred from one side to the other, creating a temperature difference. At the atomic scale, an applied temperature gradient causes charge carriers in the material to diffuse from the hot side to the cold side. This effect can be used to generate electricity, measure temperature, or change the temperature of objects. Because the direction of heating and cooling is affected by the applied voltage, thermoelectric devices can be used as temperature controllers. The term thermoelectric effect encompasses 3 separately identified effects: the Seebeck effect, the Peltier effect, and Thomson effect. The Seebeck and Peltier effects are different manifestations of the same physical process. Textbooks may refer to this process as the Peltier-Seebeck effect. The separation derives from the independent discoveries of French physicist Jean-Charles Athanas Peltier and Baltic-German physicist Thomas Johann Seebeck. The Thomson effect is an extension of the Peltier-Seebeck model and is credited to Lord Kelvin. Joule heating. The heat that is generated whenever a current is passed through a conductive material is not generally termed as thermoelectric effect. The Peltier-Seebeck and Thomson effects are thermodynamically reversible, whereas Joule heating is not. Seebeck effect. The Seebeck effect
is the electromotive force EMF that develops across 2 points of an electrically conducting material when there is a temperature difference between them. The EMF is called the Seebeck EMF or thermo-electric EMF. The ratio between the EMF and temperature difference is the Seebeck coefficient. A thermocouple measures the difference in potential across a hot and cold end for two dissimilar materials. This potential difference is proportional to the temperature difference between the hot and cold ends. First discovered in 1794 by Italian scientist Alessandro Volta, it is named after the Baltic German physicist Thomas Johann Seebeck, who in 1821 independently rediscovered it. Seebeck observed what he called thermomagnetic effect, wherein a magnetic compass needle would be deflected by a closed loop formed by two different metals joined in two places, with an applied temperature difference between the joints. Danish physicist Hans Christian Ørsted noted that the temperature difference was in fact driving an electric current, with the generation of magnetic field being an indirect consequence, and so coined the more accurate term thermoelectricity. The Seebeck effect is a classic example of an electromotive force, EMF, and leads to measurable currents or voltages in the same way as any other EMF. The local current density is given by the formula given. For those of you interested, if you want to see the formulas, please visit the thermoelectric effect article in wikipedia.org. Applications. In practice, thermoelectric effects are essentially unobservable for a localized hot or cold spot in a single homogeneous conducting material, since the overall EMFs from the increasing and decreasing temperature gradients will perfectly cancel out. Attaching an electrode to the hot spot in an attempt to measure the locally shifted voltage will only partly succeed. It means another temperature gradient will appear inside the electrode, and so the overall EMF will depend on the difference in Seebeck coefficients between the electrode and the conductor it is attached to. Thermocouples involve two wires, each of a different material, that are electrically joined in a region of unknown temperature. The loose ends are measured in an open circuit state without any current. Although the material's Seebeck coefficients S are non-linearly temperature dependent and different for the two materials. The open circuit condition means that inverted delta V equals negative S inverted delta T everywhere. Therefore, the voltage measured at the loose ends of the wires is directly dependent on the unknown temperature, and yet totally independent of other details such as the exact geometry of the wires. This direct relationship allows the thermocouple arrangement to be used as a straightforward, uncalibrated thermometer, provided knowledge of the difference in S versus T curves of the two materials and of the reference temperature at the measured loose wire ends. Thermoelectric sorting functions similarly to a thermocouple but involves an unknown material instead of an unknown temperature. A metallic probe of known composition is kept at a constant known temperature and held in contact with the unknown sample that is locally heated to the probe temperature, thereby providing an approximate measurement of the unknown Seebeck coefficient. This can help distinguish between different metals and alloys. Thermopiles are formed from many thermocouples in series, zigzagging back and forth between hot and cold. This multiplies the voltage output. Thermoelectric generators are like thermocouple, thermopile, but instead draw some current from the generated voltage in order to extract power from heat differentials. They are optimized differently from thermocouples using high-quality thermoelectric materials in a thermopile arrangement. To maximize the extracted power, though not particularly efficient, these generators have the advantage of not having any moving parts. Peltier effect. When an electric current is passed through a circuit of a thermocouple, heat is generated at one junction and absorbed at the other junction. This is known as the Peltier effect, the presence of heating or cooling at an electrified junction of two different conductors. The effect is named after French physicist Jean-Charles Athéniez Peltier, who discovered it in 1834. When a current is made to flow through a junction between two conductors, A and B, heat may be generated or removed at the junction, A typical Peltier heat pump involves multiple junctions in series, through which a current is driven. Some of the junctions lose heat due to the Peltier effect, while others gain heat. The thermo-electric heat pumps exploit this phenomenon, as do thermo-electric cooling devices found in refrigerators. Applications. The Peltier effect can be used to create a heat pump. Notably, the Peltier thermoelectric cooler is a refrigerator that is compact and has no circulating fluid or moving parts. Such refrigerators are used in applications where their advantages outweigh the disadvantage of the very low efficiency. Other heat pump applications, such as dehumidifiers, may also use the Peltier heat pumps. Thermoelectric coolers are trivially reversible in that they can be used as heaters by simply reversing the current. Unlike ordinary resistive electrical heating, or Joule heating, that varies with the square of the current, the thermoelectric heating effect is linear in current, at least for small currents, but requires a cold sink to replenish it with heat energy. This rapid reversing heating and cooling effect is used by many modern thermal cyclers, laboratory devices used to amplify DNA by the polymerase chain reaction, or PCR. PCR requires the cycling, heating, and cooling of samples to specified temperatures. The inclusion of many thermocouples in a small space enables many samples to be amplified in parallel. The Thomson effect. In different materials, the Seebeck coefficient is not constant in temperature, and so a spatial gradient in temperature can result in a gradient in the Seebeck coefficient. If a current is driven through a gradient, then a continuous version of the Peltier effect will occur. This Thomson effect was predicted and later observed in 1851 by Lord Kelvin, William Thomson. It describes the heating or cooling of a current-carrying conductor with a temperature gradient. If a current density is passed through a homogeneous conductor, the Thomson effect predicts a heat production rate per unit volume. The Thomson coefficient is unique among the three main thermoelectric coefficients because it is the only one directly measurable for individual materials. The Peltier-Seebeck coefficients can only be easily determined for pairs of materials. Hence, it is difficult to find values of absolute Seebeck or Peltier coefficients for an individual material. If the Thomson coefficient of a material is measured over a wide temperature range, it can be integrated using the Thomson relations to determine the absolute values for the Peltier and Seebeck coefficients. This needs to be done only for one material, since the other values can be determined by using pairwise Seebeck coefficients in thermocouples containing the reference material and then adding back the absolute Seebeck coefficient of the reference material. Ignoring all the scientific jargon, you can deduce from this article that there are working methods, concepts, and technologies that can be directly used to make devices, to fabricate devices that can make cooling, heating, and electricity from temperature differences. As you can read in this article, make devices that can cool a space using electricity, heat a space using electricity, and also you can create current and voltage using mainly, I believe, heat, but also cold temperatures. Although these devices are probably quite complex and difficult to fabricate at the residential level, they are nevertheless possible to create. There are devices that you can readily purchase or assemble that have very little or no moving parts, that can act as air conditioners, for example, that can act as heaters. And you can use also these concepts for building basically residences or places of dwelling. You can use the concept of a heat sink, for example, such as those seen in computer motherboards for CPUs or central processing unit. They have a usually aluminum piece or part that has many louvers for air to go through and to cool the entire metal structure, therefore cooling the CPU to a very high degree. So you can apply this concept to home building, room design, etc. I will leave it at that. This has been Living Off the Grid in the City, the radio show. And please look into these concepts with more detail if you are able, and if you can understand and apply and maybe practically build some of these devices and technologies using these very valuable concepts of thermocouple and thermoelectric. Thank you very much.